İkinci ödevden konuşuyordun hocam sanki ben geldiğimde.
Okay, let's get started. So the second assignment will be announced, I think this Friday. So we are making the last final touches on that. It will be about synchronization. Hence, it's important that we move as fast as we can this week. And by the way, Friday is 23rd. But I intend to have an extra leg, for 23rd, but I will still hold the lectures to keep the sections synchronized. Otherwise, things get really out of hand, okay? So let's get started. So we were talking about synchronization, right? And everything starts from, let's remember that we had this issue of a shared variable, right? A shared variable is a variable, okay, that is accessible by multiple threads or processes, okay, okay, and concurrently, okay, that's what we call a shared variable. And you can see that this shared variable can exist only in the it can exist as a variable sanction, okay, or like heap, okay, but it has to be a global variable that exists in one of these sections, but it cannot be a local variable, because local variables are allocated in the stack, which is different, okay. So when we were accessing to shared variables, we have a problem that's called a race condition, okay. And with the main problem that we have here is that we have basically concurrent access to shared variable, okay. And this access, what we mean is that there has to be a writing access, okay. So when we are if we have a shared variable and we are accessing only in read only, then there is no race condition. But whenever we start basically accessing them in the write mode, then race conditions can happen. And you remember that in the race condition case, the main problem is that the results, okay, basically can be wrong and also undeterministic. Okay, so that's basically it can be wrong and also undeterministic. Okay, and then we discussed critical sanction. Okay, so in case you're wondering why I'm writing so bad, it's because if I put my tablet off, on my desk, then you'll be seeing the screen, not myself. So that's why it's a little bit difficult. And what we call as critical sanction is the code, the portion of the code that accesses the shared variables. Okay, that's now along with this. We then moved on to basically methods, how we can solve the race conditions. And this is the main topic, and this will be the topic for your second assignment as well. So as Onur Hajova has already started, when we have these race conditions, there are a number of ways that we can solve. So we started with locks, okay? And meaning that if you have a critical section, so if this is my code, in here I have my shared variable, okay, and then here in some part I have the critical section, okay, and in this critical section what we can do is we can force that before, since this is series of code, I can decide to get a lock here, okay? And if you're running like this, and then unlock here, okay? That's the idea of a lock. So we already had shown how we can implement locks, okay? And we can implement locks in a basically in a way that's called what we call spin locking, okay? Okay. In the lock, what we have is we have again a shared variable, shared lock variable, okay? Okay, which takes 0 or 1. And then we have this spin locking. And spin locking means, you check the lock variable. If it's 1, which is set, then, you loop in a while, okay? So it's basically in the spin locking case, if you remember, this was while kind of this, lock variable is 1, and that's it, okay? So that's spin locking. It's basically trying this over and over. And as Onur had shown, basically this simple spin locking, if you implement this with a simple, straightforward way, then we will have a problem. And the problem being that this lock variable here, okay, this will also lead to a race condition. Okay. Hence, we are back to square one, meaning that we couldn't, when we were trying to solve the problem that we are trying to basically, while we tried to solve the problem, we ended up having the same problem again. So we need to find some other methods, and I will, like we have discussed, that this can happen in another way, which is we can have spin locking, okay, using some help from hardware, like using a compare and exchange instruction that's provided by the CPU. Hence, this solution requires, basically, this is a hardware-based solution, okay? So if you're, and what this did was the compare and exchange instruction. It would check the status of a variable in the memory, and it would exchange it only if it has a certain value. Okay, so that's basically, and it does this in an atomic way, meaning that there can any context switches that may happen in between them is actually prevented. Okay. So this was kind of like where we had left, and let me now move on to basically our other top two slides. This was just a fast refresher. Oh, okay. Let's see. Okay. God damn it! This is okay. Okay. So with the okay. So when we implemented these locks, the key thing was that this lock and unlock actions must be implemented in an atomic way. Okay, meaning that they should not be able to, we should not be able to interrupt them during execution. No context switches. Okay, either this whole function should be executed in all, or it should not be executed at all. Okay, so as we have seen, we can have some help from CPU, okay, like using a compare and exchange instruction that we have seen. There's also like a test and set. This is again like another type of basic instruction, which tests the value of a memory variable and then sets it if it's, for example, 0. Okay, this is one way to do though. Another way is actually to disable interrupts. Okay, and anybody has any idea why disabling interrupts would prevent a context switch from occurring? Hmm? Well, I mean, like you know that we have this timer, and this timer would send us basically interrupt exactly. And with this, then if you disable the interrupts, then you would effectively disable any context switches that may be taking place. Okay.
Hocam, a
So
funny tidbit is that they actually do this in some parts of the operating system code.
yes, exactly. No, I mean, I think it's good to do that, but this is something that's too dangerous to be handed to the user. Okay.
Yes, for sure.
Because I mean, you can see that like when you lock, okay, disable interrupts, and some funny thing happens, the user forgets to unlock, then there you go, the whole operating system is completely disabled. Okay.
Time to reboot when that happens.
Exactly. That's your only chance. You lose your control. So as I said there, this can only be implemented at the kernel level because, oh God, I'm sorry for this. So disable. So I have to disable my interrupts, like such as phone, and you can see that this is also can be inefficient on a multiprocessor system. Well, let's say that your CPU has 4 cores. When you disable interrupts, then it means that you're disabling the interrupts for the remaining 3 cores as well. Okay, so this is actually it's also not desirable. And what's more, uh, you may have many locks in the system. For example, imagine you have like two different applications, okay, and one of them needs to get the lock for his shared variable. Another process maybe needs to get the lock for his shared variable, okay. But when you disable them, then like they use this disable interrupt solution, then you don't distinguish between two processes who may be accessing completely different locks. Okay, so this is I hope this is obvious that we will have many locks in the system which may be protecting many different shared variables. But with this way, when you lock, all the shared variables in the system are now prevented. Okay, so no context switch is being basically made. So in that sense, for example, you cannot distinguish between blocks from different bank accounts when you're accessing, for example, when you're trying to withdraw money from your bank account, then it will put a lock onto the system such that even someone else who's accessing his own account will not be able to access it. Okay, so this is really bad. So I will go over this like these implementations. Onur Hoca has discussed them, and like the slides are here just for you. Now with the spin locking, it's nice, but it's actually not an efficient way. The reason being the following: like here's an example that some people may get offended, but the synchronization issue is similar to basically two guys sharing the same house. Okay, and you like here, and then another guy's here, and in this room, like you can live concurrently. There is no problem, right? But then there is some part of the house that you don't want to be shared. Okay, you can share the living room, you can share the the rooms, the kitchen, but there is one portion of the house which you do not want to be share with your friend. Anybody, any guesses on this? Dennis knows what it is. He knows it. Any guesses on which part of the house that you never want to share concurrently with your bathroom? Exactly.
Bathroom.
Exactly. So let's call this, this bathroom, okay? And what you want is, and this is your critical section, right? Okay. Well, I mean, you can just go so there's some variable here in the bathroom that you want to update. Okay, this is where it gets funny. And the code that you basically do your stuff in the bathroom, that's the critical section, right? And what do? The lock mechanism, it's you have this door here, and with this door, this is okay. So that you have a door, and when you get in, then you lock it, right? And then the other guy can try it. And what happens is, remember, it runs this guy a bit, and then this guy a bit, and then so it gives CPU to both of them. There's the operating system switches back and forth. So when the first guy is in, let's say that this first guy, sorry. So our first guy is in here, okay? And he locks, okay? And the second guy comes. Now this guy is running his own critical section code, okay? And this guy comes and he tries, so you give him 50 milliseconds to work on his shit, okay? Beep, okay? And then this second guy comes, okay? And then he has his own 50 milliseconds. And what does he do in that sense? Well, he tries over and over, is it open? Is it open? Is it open? Okay, that's what we call spin locking. Now, this is good. It can even be fun with when you have two. But imagine what will happen if we had the same solution at the department. Okay, so in this case, now all of a sudden, you have one guy occupying this critical section, but then you have, maybe 50 guys, okay, that are trying to basically in spin locking, okay? So you can see that, now when I give this, here's the guy who is in, so he's running his critical section. But then, you make a context switch, and here's thread 1, okay? And he gets his 50 milliseconds trying the door. The second guy comes, he basically tries the door, and etc. So when you look at it, all these 50 guys, or in this case, 5 threads, will spend 250 milliseconds on just trying whether it's locked or not. Okay, they still use the CPU. Okay, if you had given that CPU to this guy, he would have finished over a long time ago. Okay, that's why this is a solution, but it's not an efficient solution. Okay. So, but it's nice because, as we will see later, we will build primitives to build higher level synchronization constructs, and we'll start it right now. Now, what I will at this time, you may be, you have lost your hope that this is a solution that's really too difficult. There's no algorithmic solution for this, and now I will prove you that this is actually not the case. And here's this algorithm called Peterson's algorithm, and this is implemented for 2, but you can generalize to basically many threads as you wish, except that you have to know this number in advance. And this actually solves this problem algorithmically. Okay, and so here's the code that we have here. So we have p-lock, Peterson's lock, and Peterson's unlock. Okay, 2 functions, and we have 2. In this case, we know that we will be synchronizing 2 threads. Okay, so we have called a flag of size 2, and we have a turn. Let's go over them with this solution. So here we have thread 0 and thread 1. Okay, and we have these 2 variables called flag and turn. And what we do is the turn, okay, this is thread 0 and 1, okay. So the turn equals I indicates that TI is allowed to get it, okay. That's what we have. And flag indicates if a certain thread is ready to enter the critical section. Okay, so for example, if we are running our thread 0 and thread 1, and they are not in their critical section, they are not interested in getting the critical section. Okay, in that case, both flag, and you can see that their both flag values are 0, and this is the turn here. Okay, this is a shared variable that we will be looking for. Now let's see what happens when we try to get into a critical section by calling plog. Okay, this is where we want to get into the critical section. And what we do is we set flag ID to 1. Okay, this indicates that flag ID, that is like a flag 0, I set this to 1, meaning that I am interested in getting into the critical section. Okay, and then you will say turn is the other one. So if I'm 1, then this will be 0. If I'm 0, this will be 1. Okay, and then you have this loop saying that if the other one is interested and the turn is also others, or his, then you loop. This is spin locking. Okay, that's what we do. That's pretty simple. And in the case of unlock, it's pretty simple. You just set flag ID to 0. Now you can see that with thread 1, so in the case of thread 0, like this other is actually equals to 0. Okay, here the other equals 1, right? And you can see that flag this one is updated only by thread 0, whereas this one is updated by thread 1. Hence, the flag array, there is no race condition because each of them is updating a separate part. Okay, but we will have, since they will both be updating the turn, we will have a race condition on updating this turn value. Okay, because this is where they can both write on this. So now let's look at what can happen. So here you can see that let's say that both thread 0 and thread 1, they both set their flags to 1. Okay, meaning that they want to get into the critical section. Okay, and then after that, they will try to set the turn. And note that in this case, like this thread 0 will try to set the turn to 1. Okay, whereas thread 1 will set the turn to 0. Okay, so and there will be a race condition. Okay, regardless. And let's say that thread 1 writes first. If the thread 1 writes first, it will first write 0 into the shared variable. Okay, and then thread 0 writes second, and then after that it will write 1, and hence this turn will be 1. Okay, in here you can say that, well, I mean, what if it happens otherwise, right? And I will, that's the next slide. Okay, let's say that this happens. Now, when this happens, then you can see that with this condition, flag 1 is 1 and turn is also. So thread 0 loses and it starts spin locking. Okay, whereas thread 1, now since the turn is not 0, then it will move on and thread 1 will enter its critical section. Okay, so this is a case where thread 1 wins. And when thread 1 exits, then it will set the flag 1 to 0. This spin locking will break, and then it will enter its critical section. Okay, and when it exits, then it will also, you will get back to here. Now, so this is what happens like when thread 1 writes first and thread 0 writes second. Now, what if okay, the opposite happens? It's again the same thing, but this time thread 0 writes first and thread 1 writes last, and as a result, now the turn remains as 0. possibility. We have a race condition, so this is the other possibility.
Hocam kesilme oluyor ama sizde sesiniz arada gidip geliyor.
Okay. Did you? I'm not sure why it happened. So what I can do is I can come back and talk. Let's see. I can switch to my other computer. Just give me a second.
Görüntünüz de donmuş gibi görünüyor hocam.
Şu an geri geldiniz hocam. Başka bilgisayarda.
Pardon, ikinci bilgisayardan geldim. Oh, I got it. Okay, that's good. Sorry, let me see. Can you hear me now?
Evet hocam.
Yes, hocam.
My pen laptop has frozen. Okay. So let me go through this Peterson's algorithm here. Okay. Let's see if I can go. So let's say that we remember that when we have these flag variables here, the flag variable, the flag 0, it's updated by thread 0, okay, and flag 1 is updated by thread 1, okay, and hence there is no race condition on them because only one of them is updated. But with the turn variable, we have a possible race condition. It's because they are both trying to update the same variables here, okay? And as a result, so let's say that at here, both thread 0 and thread 1, they want to enter the critical section and they call the P lock, okay? Thread 0 will call this P lock 0 and the thread 1 will call this P lock 1. And as a result of this flag 1, which displays that they are interested in getting into the critical section, then we will have both of them to be set to be 1, okay? But when it comes to turn, then we will have a race condition, and in this case, let's assume that thread 1 writes first, okay? It will write 1 into that, and then it will write 0 into the turn, and then thread 0 writes second, and it will write 1, okay? And as a result, at the end of this, then we will have a 1 here, okay? And as a result of this, then you can see that since this is 1, we will have thread 0 will end up in spin locking here, whereas thread 1 will go forward and into its critical section. So it will run its critical section here, whereas thread 0 will be blocked, okay? And when thread 1 unlocks, okay, it will set flag 1 to 0, okay, like this, okay, and this will then break this, and then thread 0 will get into its critical section, okay? Is this clear now? Yes? Okay.
Yes, hocam.
Now, okay, let's see. Okay. And in the case of like, what if the in the race condition, thread 0 writes first, okay? The drawing. Okay. What if thread 0 writes first and then thread 1 writes last? Now, in this case, the turn variable will end up being having this value of 0. Okay, again, a race. And in this case, thread 1 will lose. So as a result of all this thread 1 will start spin lining, and thread 1, okay, will then basically get into here. And this is, oh, there's a, this should be 0. Okay, and it will get in, okay, and it will go as such. So this is an interesting algorithmic solution, and it's because we're not preventing the race condition to happen, right? But through this, we can ensure that only one of the threads get into its critical section while the other blocks, okay? So this is like, again, algorithmically very interesting. Now, okay. Now, let's discuss basically how good is this solution. The first thing is like, we guarantee that, there's mutual exclusion, meaning that if one thread, okay, enters the critical section, then the other one is blocked. Okay, that's nice. And then we'll have these two other ones, okay, 3 other things, but I will discuss them, come back to them later. Okay, and there is, it's like, you note that there is no strict alternation required between the threads, meaning that T0 can get in its critical section like 3 times before thread 1 and using it. So it's not just like 1 and then the other one, 1 and then the other one, and so on. Okay, and it requires that threads alternate between critical and remainder sections, and it can be extended to n threads, but only if we know n in advance. Okay, and this is again like something that I want you to think about. And this note that whatever we do here, it is also valid for processes. And as a matter of fact, when you're, for example, like thinking about the pipe implementation, which is a shared variable, this is basically what is happening in there. So let me discuss this. Okay.
Jam, so the interesting part here is that in fact we achieve mutual exclusion without having to use atomic instructions, right? Like compare and exchange. This works even when we don't have atomic instructions.
That's correct. That's correct. It doesn't require any help from the hardware. Okay. So let me just see. So with this, we arrive at mutexes, okay? And mutexes are basically, it's an extension of locks. And what we really want is, we want our, if when a thread wants to acquire a lock, if it fails, it should be removed from the ready list at all, okay? And when I say this, this is like, it's because, you know, remember, why did we have a problem in the system locking? We had a problem, it's because, you know, the guys who were not able to get the lock were still able to get the CPU, okay? And hence they would then waste their time on the CPU by spin locking. What if we do the following? When you try to get the lock, and if you fail, what if the operating system puts those threads, okay, removes them from the ready list and puts them onto the wait list, okay? Meaning that, you know, it would never context switch to that one until lock becomes available, okay? So this is basically, this is the main innovation behind mutexes, okay? And let me see if I can.
Hocam spin nokta bekleyeni başka bir yere alıp bekleme yapılan thread'i mi release etmiş oluyoruz?
No, if you, when you try to get the lock, okay, let me just finish this and we'll continue, okay?
Okay hocam.
Okay, so let's say that, you know, let's see if I can, okay. So let's say that we have thread 1, okay, and it checks the lock state, and, you know, then it sets the lock to locked, okay, and it enters its critical section. And after that, a second thread comes. It checks the lock state, and if it's not available, then it adds itself to the wait queue, okay, meaning that we will never come back to him, okay, until the lock is unlocked, okay. And then, you know, when say that a third thread comes, again it tries to get the lock, it's not available, you put him to sleep as well, okay. And then when thread finishes its critical section, okay, and unlocks, then it wakes one thread from the wait queue, which can then try to get the lock, and this time it will now grabs the lock and it will enter its critical section. Now, this corresponds to the following. In the case of our this roommate example, we said that, you know, like there are two guys, so you're basically running them one at a time, okay, 1 minute at a time. And when the first guy gets the lock and then gets into its critical section, and then you make a context switch to the basically second guy, and then if he doesn't try to get the lock, he can run, okay? But if he tries to get the lock, then you put him to sleep, okay? Meaning that you will never wake him when you try to give the CPU to him. And then, you know, you basically let the guy in the bathroom run, okay? And whenever he unlocks, then you wake the guy who was sleeping on that lock, okay? Is that clear, Taha?
Evet hocam, teşekkürler.
Okay. So that's the main thing. So we kind of like, it's now a much more efficient basically implementation of this. Now, this lock idea is nice and it's simple, but what if we have like, you know, we have a lot of other cases, for example, like there may be a lot of cases where, you know, it may be okay for threads to read the data, but you can only may only prevent one, like allow only one thread to write. For example, take a reservation system. On the reservation system, you know, like you may have a lot of readers who will just, you know, check the status of a particular seat, okay, whether it's available or not. But when somebody wants to buy, which is the case that you want to change it, you want only one guy to update this basically status of the seat. But you want to have many, maybe, you know, like any number of readers who wants to access and see whether it's available or not. Now, if you do this with a lock, then there's no other way, because in this case, you know, if I put a lock around this, accessing this reservation variable, the seat, for example, then you will also, you cannot have multiple readers available at the same time, okay? But what you want is, you know, multiple readers is okay, but, you know, a single writer is okay, but two writers should not be okay. Or when the writer is updating, for example, the seed is fine, then we should also prevent the readers, right? So this is a case where it's like, you know, when you try, if you think of it, if you try to do it with lock, then you will be having in the critical section either basically only one reader or one writer at a time, which is very inefficient. Okay, this is one case. And the second thing is like, you know, again, with the bank account, in the case of a bank account, then you may have, again, you want to have different locks for different users, okay? And then again, if you're just reading it, then it should be fine, but we should only prevent multiple writes at any time, okay? So we will again now discuss basically what these problems are. And so we will move on to basically the topic of semaphores and monitors and condition variables. So let me switch to that. So we will move on to our first, basically, kind of tricky topic on, like, you know, complex synchronization primitives, you know, called semaphores. This is very interesting, and we have seen basically what the problem was. And so let me show you this readers and writers problem, where we want to have, like, we have, say, a shared variable, okay, and what we want to do is we want to have any number of threads to read it, but only one thread to write it, okay? Now, in this case, it will be, you know, if I try to do this lock variable with the reader as such, then you cannot have more than one readers at a time, okay? And when the writer is active, for example, by setting this value, then I also want no readers inside that, because then it will be wrong, that the reader may get some inconsistent data. So this is something that's not possible with the locks. So this brings us to semaphores. Now, what's a semaphore? This is again another, like, you know, when I was taking my operating systems course, just like you, there were a couple of terms that completely mind-boggling me. The first one was preemption. Okay, it took me a whole year to get what it is. Okay, which was, and then the second one is was semaphores. Okay, this is again another, you know, magical kind of thing. And in here, then this is basically what's being, like, this is, you can say this is the, what we call the semaphore. This appears in the railways, and this was designed by Dijkstra in 1960s. And initially, basically, well, a semaphore is actually a shared counter, okay, and which is initialized. And there are just two operations on a semaphore, okay. And these operations have three different ways, which again contributes to its confusion, okay? And we will see. In Byte, I will do with, like, since this is a counter, okay? It can be a down or it can be a up, okay? So you can, with a semaphore, you have three possible. You initialize it, you can do a down, or you can do a up, okay? But you cannot check the value of a semaphore, okay? And down also appears as wait, okay, and V appears as a signal. And basically, this operation, which is also, okay, in Dijkstra's basically original implementation, it was like P, which comes from Dutch because he's a Dutch guy, proberen or probe or meaning test. And this is an atomic action, basically, to wait for a semaphore value to become 0 and then decrement it. And V or up or post or signal, okay, these are all equivalent functions in different implementations. it means, verhogen in Dutch, or increment, and it means, increment the semaphore value by 1. At this time, you get really confused what the hell it is, but I'll just explain this. So a semaphore is something like this. Like imagine, like a semaphore is like it's a table, and on this table you put, say, a token. Okay, when you initialize a semaphore like with 1, that means that you put 1 token on your table. Okay, and with this, then you can have basically down or wait. Okay, wait means like and here we have our wait. Okay, when you call this, let's see if I can run this. I'm using my, let me just tell you why I'm doing this. My tablet crashed because the PowerPoint animations that I was running didn't basically screwed up the system. So now I switched to PDF, but then with the PDFs, I cannot show you the animations that I had. So I'll try now.
Maybe hocam you can draw the animations on your tablet.
No, I don't. I have spent I have invested quite a lot on my animations. Okay. Let's see. Good. Okay. So here's my semaphore initialized with 1. Okay. And when I have a thread which calls wait or down, or like, then, it comes, and if it's a token, it takes it, and then it proceeds. So it doesn't block. Now, before the semaphore value was 1, now after the semaphore value is 0. Okay. Now a thread 2 comes, and then it also calls wait or down. Okay. And at this time, it blocks, so it's added into, basically it's into the sleeping list. The third one comes, and then it calls signal. Now signal is also up, okay? And it comes, and it gives this to that, and the thread 1 also moves, okay? So let's go do this here. So what about the shared counter? Like, before this, the semaphore was 0. Okay. Now after your semaphore value, you can also envision this as -1 because you don't have any semaphores. Okay. But you have one thread that's sleeping on the semaphore. Okay. And hence it. And when the thread 3 comes with a signal, then it comes. And before it was -1, but after it hands it over, then the semaphore value after is 0. Okay? And the third one comes, and then now it calls, and then it basically increments this, and so now the semaphore value becomes 1. Okay? So now let me come back here to these things. Okay? So we have, like, as I said, like with the semaphores, we have 2 operations. You can do a down or wait or probir. This basically probir means, to check whether you have any tokens on the table or not. Okay. When you do a wait, okay, there are 2 possibles. You can either, if you have a token, then you proceed. You take the token and you proceed. If there are no tokens, then you block and sleep on it. So you can no longer, you're removed from the redo list. Whereas V or increment or up means, or signal, okay? What this means is you're putting a token on the semaphore, okay? You're like kind of incrementing it. And when you do it, so when you do a signal, you will always proceed. You never block, okay? Because you're putting a token on the system. But as a result of all this, when you put a token, a thread, if there is a thread that's sleeping on the semaphore, it will wake him up and it will make him proceed. Okay, so that's the main idea. If you keep this, then you will have no problem. But this is basically as simple as it gets. So again, you'll be working with threads, right? So we'll have this, like in the threads, you have these three operations, okay? Semaphore init, in which you set basically into an integer value. This tells you initially how many tokens do you put on the table. Wait means I want to take a token from the table. If there is one, I will proceed. If there are none, then I will block, I will wait, okay? And post is equal to signal, or this is the case where you put a token into the system, okay? So with this, now, this is like a semaphore, you can implement locks. Like you can see that, you just initialize your semaphore with 1 here, okay? Can you see my cursor, by the way?
Evet hocam.
Yes?
Evet, görünüyor hocam.
Okay. So you initialize it to 1, and, instead of lock, you just do a wait, okay? And then here's your critical section, and you do a signal, okay? This is the idea. So essentially, a semaphore whose initial value is 0 or 1 is a binary semaphore, and mutex is equivalent to a binary semaphore, okay? And here's how we can implement this. Here we have our semaphore. We have a value. This counts the number of tokens on the table. Okay, it can be 0 or positive numbers. And then I have a thread list. Okay, this thread list, it's the list of threads that are waiting for the semaphore. Remember those threads which were coming and calling a wait, but then gets blocked, okay? So this keeps track of all, okay? So initialization is pretty easy. You set it to the initial value, this val, and then you have this wait and signal, okay? In the case of a wait, what it is, you check for this value. If it's basically less than or equal to 0, then you add it to the list of threads, okay? And then block the thread that calls, that makes this call, okay? And, after, and if this blocked, then this will be getting blocked. What about the signal? In the case of signal, you increment it by 1. And if the list is non-empty, then you go to SL, pick a thread, remove a thread, and wake him up. So when you do this wake up, then this will wake this guy who was blocked here. He will take his token and he will return, okay? So this is completely, object-oriented. You just have these two methods as such. But note that, all this init, wait, and signal, they should be implemented as atomic actions. And this is where all those spin locking and other things come really handy, because this is implemented at the kernel level, okay? So, let me see. Yes, this is, I already told you, okay. So, why are semaphores useful? So far, you may say that, well, okay, we get the point, but they can be going to a log. But what happens, if you initialize a semaphore's value to 50, okay, what does it actually mean for the, wait and signal operations? So we will now discuss this, okay? So this is a good time to basically have a break, and after that, we'll talk about basically a set of classical synchronization problems, and the producer-consumer problem or bounded buffer problem is a classical synchronization problem. And as a matter of fact, like when you think of the pipe construct, which is in a pipe, it's a shared data structure where you have like the two processors or multiple processors are basically insert new items and then remove items, okay? So this is a case where you can have actually race conditions, and if you want to implement this, then you will need such constructs. So let's have a break here of maybe like 5 minutes, okay? And then after that, we'll continue how we can solve this with semaphores. Okay. Is everybody back? Okay. So here's the first classical synchronization problem, and we will solve this with different constructs. And at this time, we will be discussing this this problem with solving them with the semaphores. It's also called the bounded buffer problem, and the problem is as follows. We have a producer and a consumer. The producer, pushes items into the buffer. We could make this as the characters on your pipe, but bananas and Homer is more fun. So this lady produces these donuts and pushes them onto the buffer, and consumers them pulls them from the buffer. Okay, so far so good. But here is the basically limitations. The producers needs to wait when the buffer is full because it says it's a bounded one, and then the consumer needs to wait when the buffer is empty. Okay, so under these constraints, and remember, this can be two threads that are accessing this, or this can be two processes and accessing the same pipe, for example. This is the same problem. So here is one implementation. Like here's the producer thread and the consumer thread. In the producer one, it loops in this while. It produces an item. And let's say that the size of the buffer is n, capital N. So if the count, so we keep track of the count, and this here we can say that this count is now a shared variable. Okay, so if count is n, then it sleeps. Okay, else it inserts an item into the buffer, it increments the count, and if the count is 1, then it will wake up the consumer. And here's the consumer. Again, it loops in this while. If the count is 0, okay, then it sleeps. There's nothing. Else, it removes an item. It decrements count by 1. And then if the count becomes n minus 1, meaning that maybe the producer may have basically was sleeping, then it would wake up the producer and then eat the item. Okay. Now, the problem that we have here is that we have two shared variables. One of them is this count, and the other one is the buffer itself, when you are like adding, inserting, or removing an item. Now let's say that let me see. Okay. So let's say that that the producer basically inserts items. Okay. And say that the consumer thread is, say that, let's see how it was. Just move this. Okay. Let's see. Okay. So let's say that this our producer is inserting items here, right? And the consumer is eating. And if at a certain point the count becomes 0, if count is 0, and then we make right before getting to the sleep, we make a context switch here. Okay, and in the context switch, then we switch to the producer. Okay, the producer produces items. Okay, and so it produces these its items. It inserts 1. Okay. And then the count becomes 1, okay? And it sends a wake up to the consumer. But the problem is the consumer has not slept yet. It was right here. It did the check here, but it did not sleep here. But it sent this wake up signal to the consumer, which will get lost. okay? And then we'll switch back. The consumer will sleep, okay? And then, you know, it will sleep here. As it sleeps, then we get back to our producer. It will produce another one, another one, another one, okay? And since it's not waking up the consumer up after that, it will the whole buffer will become full, and it will also be sleeping. So as a result, both of these threads will end up sleeping. Okay, so you can see that like you can see the main problem is that, you know, I have this count shared variable, and its access to it led to a race condition, which basically caused our system producer consumer system fail. Okay, now how can we implement this? To fix this with semaphores. Here's how it works. So the first thing is we declare a couple of basically semaphores, 3 semaphores. The first one, like, you know, we usually we declared a semaphore called named Mutex. Okay, so Mutex is not I can put this any name, but and usually the idea is if you're going to initialize a Mutex and you're going to use it as a lock, this is what we call it, just a Mutex. Okay, and then we have like 2 semaphores. Semaphore full, okay, you initialize it to 0. It says, you know, how many slots are empty, full in the buffer, and then semaphore empty, which is initialized to n. This basically initially the number of slots on the buffer is n, so that's why we did. And here's how it works. While true, we have this loop, we produce it. Now, what we do is that we do have wait empty, okay? Now, what wait empty does is, remember, empty was initialized like it's basically empty keeps track of the empty cells, okay, in the buffer, okay? When you do a wait empty, remember our table example, right? So you have this empty table, and on this table, basically we initialize it with n, meaning that since our buffer is of size n, you put n tokens up front, okay? And when you do a wait empty, you basically check whether there's any empty slots available there, okay? If there is one, then you decrement it by 1, okay? And what if there is nothing left? Then you will block, that will make you sleep, okay? And then after that, then you insert the item. But you note that, you know, when I'm inserting an item to this buffer by itself is also a shared variable, okay? So I put this wait and signal. This is essentially lock and unlock. So in order to make sure that, you know, when I'm inserting an item here, the other guy should not be trying to remove the item from the same buffer, okay? This is this may lead to, again, a problem, a race condition. And after this, at the end, we do a signal full. Remember, like what was full? Like we have 2 tables, right? One is full table, one is empty table. The full table was initially 0, okay? And at the end of this, what we do is we do a signal full, which is supposed to wake the consumer thread. Now let's look at the consumer thread here. In the consumer thread, when it comes and it tries to it needs to do a wait full on this. Remember, the wait full keeps track of, it's a table, and for each item inserted, you put a token. Okay, and if it does a wait on full, meaning that it checks whether there's a token on the full table. If there is one, it takes it, and then, you know, it uses again this lock, unlock, or Mutex kind of thing to remove this item. Okay, and then after doing this, then it has to do a signal empty. Now, what this means is, you know, after removing one from the item, then you have to put a token onto the empty table, okay? So that if the producer was waiting on this empty, it will wake them up. Okay, the same goes here. Like after putting an item, like after inserting an item here, you insert a token for the full, which if there is a consumer thread who is waiting on that, then he will wake up. Okay. So you can see that like with this, like, and this looks very simple, but it's also very tricky to implement.
Hocam threadler arası yani jump demeyeyim de threadler arası go to jump gibi geldi. Büyük ihtimalle saçma bir benzetme oldu ama neyse.
Oh, this is not jump, but this is basically, you have these two threads that are running left, right? So when you do a signal, remember, like, let's go back to the implementation. Like when you do a signal, you put a token, okay, on the table, and then after putting the token, then it checks whether there is any thread that's sleeping on that token, that's waiting on that token. If there is one, it will wake him up, give him the token, and let him go. Okay, that's what signal does. Okay. So is that clear? Like, don't feel shy not to ask questions about this, because this is a Semaphores. This is one of the most difficult concepts of this whole course. And if you have any problems, just speak up.
Hocam, it looks rather okay when there are like only 2 threads, but I guess when the number of threads increase, which one is going to flag which one? It's going to be a little, yeah, messy.
Exactly. So now let's go back to our problem of readers, writers.
But hocam, I think the nice part about the previous producer-consumer thing is that even if we had n producer threads and n consumer threads, it would still work.
Exactly.
And so it's a generic kind of synchronization on the buffer, which is a good thing. That's what I was trying to say.
Exactly. And your second assignment will make sure that you understand these concepts really well. Now let's go back to our readers writers problem. Remember that, like in that case, we had one single shared object, like a seat on an airplane. Okay. What we want to do is we want to allow any number of threads to read it simultaneously, but only one thread should be able to write to the object at a time. Okay. And it should not interfere with any of the readers. Okay. So here's the more formal thing. So here's our shared variable. So we'll have these writers, like they can have read-write access, and readers which have only read-only access. Now reader only reads the read the object. Writer threads modify the object. Okay, and writers must have exclusive access to the object, meaning that if they're while they're accessing the object, the shared variable, no other threads, readers or writers, should be able to access it. Okay. Now, to you may see that, well, I mean, when the writer is writing, like updating this shared variable, why are we preventing readers, right? For example, take that. Well, the reason is the following. Usually when you're updating this, imagine, you're saying, I don't know, like let's say I'm updating data, and then that contains multiple fields, okay? And you update one field, like say your name, but I didn't update your surname yet, okay? And if the reader was able to see it, okay, then he would see a different guy, okay? For example, let's say that in this case we have like in this object we have Yasin Erol, okay? His name is in here. And then any writer is updating it. So he updates, he wants to update it with my name, Erol Shahin, okay? But he updates the name, he changes to Erol, okay? And after that, if the reader checks what's written in here, he will see Erol, right? Okay, which is the inconsistent data. So when he's doing this updating, the writer is doing the updating, we want to make sure that the readers are not actually accessing the data. That's why the reason, okay? Now, as I said, this is basically occurs frequently in real systems like airline reservation systems or multi-threaded caching on web. So these are the possibilities. Like if we have writer is active, then all the others should not be active. Or if the reader is active, any number of readers can be active, but no writers. Okay. So this is the synchronization constraints that we have to satisfy. So here is how we can solve this. Like here is our, let's say that in this case, we have again the writer thread and the reader thread. Okay. And what we do is we have a mutex, okay, initialized to one. We have like two mutex, okay. Let's say this is called mutex, and then here we have the write. Now the write here, okay, this write semaphore, which is initialized to 1, it wants to ensure that it basically it ensures that there's only one writer when the writer is away, basically accessing it. No other guys should be accessing that. So let's look at the writer code to see how it's being used. Here's writer code. It does a wait write, okay, and then it do writes and then signal write, okay. Now this is like it's using the write as a signal since it was initialized to 1 here. And what it means is, when a writer, like initially, there's only one token on the write table. The first writer calls, gets the token, starts its writing do write, okay? And while it's doing this, if another writer comes, he will be blocked. He will call a wait, okay? He will be blocked. A third writer comes, he will be blocked too, okay? Until the first writer who had the token calls a signal write. When he does a signal write, it means that he puts the token back, and one of the two writers who were blocked on this, who are waiting on it, he will then wake up and then will continue, okay? So the writer thread is pretty easy, okay? This is simple. Now, the fun thing happens in the reader thread. In the reader thread, we have to be a little bit careful. The first thing is, note that we need to keep track of the number of readers that are active in this, okay? Why? Because, because we have to ensure that if there are, like if I do not keep track of how many active readers, then how am I going to let the writer to go in, okay? And this is basically why we have a variable called read count, okay, or this is reader count. You initialize it to 0, and now since this will be updated by, this will be incremented by the readers when they are entering, and they have to be decremented after they exit the critical section, okay. But since this read count is a shared variable, I also declare a mutex semaphore, okay, which is set to 1, to basically to control access to it. So here's how it works. The first thing is like, here we have like, here's the part that the reader executes before reading. So here's the part where I do the read, okay? Here's what I do before, and this is what I do after, okay? Now in the before part, since I'll be checking, like I'll be using this read count, I basically lock and unlock the access to read count, okay? Because here, this is a place where I will be incrementing my read count, okay? And at the end, I will be doing decrementing my read count. And if I do not, do not protect them with this mutex, then I will have race conditions. So you'll be counting the number of readers wrong, okay? So this part is fine. So you increment the read count and then you decrement the read count. But then we do something else, like, the first reader, if the read count is 1, okay, then we do a wait write. Now, why do we do this? We do this because when the first reader comes, then we want to prevent any writers to get in, right? because when the reader is in, the writer should not be allowed in. And that's why we do a wait write, which basically takes the token from that and then blocks. And so this is basically what we do, the check. And at the end here, in the second part of the reader code, we decrement it. And if the read count is 0, it means that the readers are off. Then we do a signal write in order to make sure that maybe there were writers who are waiting for us. So we'll just let him, then wake him up and then go ahead. So this is like this readers, writers, like if you were in the auditorium, the example is like I would say as such. So the readers are students, right? Okay, the students, there can be any number of students in the auditorium, no problem, okay? But then there's the janitor who wants to clean, mop the floors, okay? And what he has to make sure is, if there are no students, then he can do that. If there are students, then he has to wait for them, okay? And the way we do this is, basically this wait write and signal write is like, switching the light on and off, okay? So basically, if the writer wants to come in, like he basically checks it, he turns it on, and then does his stuff, and he turns it on. With the readers or with the student who gets it, the first student who gets in the auditorium turns the light on, okay? This is what we do with this wait write. And then the last student who exits the auditorium, he turns the light off so that, if there is any janitor waiting to clean the auditorium, then he can get it, okay? Any questions on this? No? Okay. Well, okay. So to summarize, the signal never blocks, because signal or up or verhogen, okay, it means you're putting a token on the table. You put it, you go, okay, and the token may wake some sleeping thread or person. Wait, it may block, okay, it would block, and then if the wait means, I want to get a token if possible. If there is a token, I'll take it, decrement it by 1, and then proceed. If there are no tokens left, then, well, I will wait. Okay, I will. And initialize, well, it will initialize the semaphores values to n, fine. Here's the thing that's basically, let me give you a hint. When we ask, questions in the exams, solve the synchronization problem with semaphores. And whenever I see something like if semaphore equals I, this is a sign that this guy has no idea what he's talking about, okay? You can, I will be very happy to grade the whole paper, the whole question with 0, because he has no idea. This is the first thing that you should remember, okay? You can do a signal, you can do a wait, you can do init, that's it. You cannot check the value. That's basically key idea, okay? So now let's go over some basically synchronization patterns, and this will actually make sure that how well you have understood this. Okay. The first thing is yes.
There was something that I found interesting when I was a student that I want to talk about semaphores. So something interesting with the tokens is that you don't actually need to have tokens to put them on the table. So you might not have anything to do with the semaphore, but you can just come and signal 100 times or something like that. So you don't need to wait before being able to signal. That's what I wanted to say.
Exactly. That's a good point. So it's the number of tokens that you can generate is basically large, right? Anything. Okay, so now let's look at basically, we will go over a number of synchronization patterns. And the first one is called signaling. And by the way, like all these examples that we took are available from this little book of semaphores, which is like, it's a free book at this, available at this line. and it has its incredibly, it has all kinds of synchronization problems, okay? And what's the signaling? Well, signaling is the simplest use of semaphore. What we want is one thread sends a signal to another thread to indicate that something has happened. And for example, let's say that I'm running my PowerPoint, okay? I want to say print it to my printer, okay? And but the code, so what I have to do is my PowerPoint has to first write my presentation into a PDF, okay? I have to wait for this to happen. And then maybe there's another process which would read the PDF and send it to the printer, okay? So in this case, your PowerPoint needs to signal the printer daemon that its job is over. Okay, it's basically one guy sending a signal to the other one that something has happened, okay? So here is basically like, again, like this is, again, the problem that we have here. So here we have thread A and thread B, okay? And let's say that, like again, in a simpler case, that the statement A1 reads a line from a file, and statement B1 displays it on the screen, okay? So in this case, I want to make sure that B1 is executed after A1, despite the fact that thread 1, thread A, and thread B, they're running concurrently, okay? So you have no control. Maybe, like if you just let thread A and thread B run as they are, okay, then B1 may execute well before A1, okay? And you want to prevent this. You want to make sure that A1 is executed, sorry, B1 should be executed only after thread A completed the execution of A1, okay? That's basically what we do. Now, how do we do this? Any ideas? Well, usually I would do this more interactively, but let me just go here. So this is the simplest way that we can do here. We can declare a semaphore, initialize it to 0, okay? And with thread 1, it would wait on the semaphore, okay? And with thread A, you put a signal after A1. What this means is if thread B arrives here first, then it would call the wait semaphore, it will be blocked, okay? It will be blocked until thread A comes, executes A1, and then sends a signal, after which it will release this and it will execute B1. What if it's the other way? What if thread A comes here, executes A1, and then do a signal? When it does a signal, you remember it's putting a token on the table, okay? And it will move on. Maybe it will exit here. And thread 1, when it comes here, when it does a wait, well, it will grab the token without getting blocked, and then it will then execute B1. So in either case, we ensure that B1 executed after the exit A1. Okay? So this is why we call synchronization. We are synchronizing the concurrent executions of threads that are running like as separate control flows.
Hocam, in this question, thread A can run multiple times before thread B starts, right?
No,
there are no guards in thread.
No. In this case, this is not a while. They just run once.
Okay.
Okay, good. So this is the signaling. Now then there we have the rendezvous problem. Okay, in this case, we have thread A, A1 and A2 here, and B1 and B2 here. Now what I want to do is, after executing A1 and AB, this is like two guys, okay? They're in separate places, but you want to make sure that when I arrive here, if I'm early, I have to wait for the other guy to arrive here, and after that we move on, okay? You kind of come here. If one of them is early, then you have to wait for the other one, okay? And then after that, you can go on your own way. This is the thing that, after executing A1, okay, then basically, of course, like here's the condition: B2, okay, B2 should be executed only after A1, and A2 should be executed only after B1. Okay, B1 is completed. Okay, so you can see that this is like two-way signaling. They have to wait for each other. Okay, after executing these two statements. So let's say that, and beyond this, there is like they can run as they wish. There are no more constraints. So here is like, we can declare two variables, A arrived and B arrived. Okay, and we can initialize them as 0. Okay, and with this now, how can we do this? Like, of course, when you look at this, you can say, well, this is really easy problems, right? On a semaphore, all I can do is a wait or signal, and I just have two semaphores. What are the possibilities that I can get this wrong? So let's talk about it. Any ideas on how we should proceed here? No. Okay. If I was in the auditorium, I would have made this much more interactive. But let's move on. So here's how it would work. So for A, I would do a wait B arrived here, and then after finishing A1, I would do a signal A arrived. And for B, when after executing B1, it should signal B arrived, and after doing that, it should wait on A arrived. Okay, so with this, you can see that let's say that A1 comes, it signals A arrived, and then B has not started yet, so it will block on B arrived, and then B comes, executes B1. Okay, and then it will then signal B arrived. Oh, sorry, this should be the other way. Okay, this arrow should be the other way. So it should then wait this thread A, which can then continue on its way. And when it does an wait A arrived, it's already 1. So it will then move with B2. Okay, you can see this. Now, with this, this looks easy, but what if, we change the order here? What if we do this? What if, after A1, I would wait for B arrived, okay? And then, in this case, like B1 is here, and it will say signal B arrived. And with A, it will then say signal A arrived and wait A arrived, okay? How would this do? Now, in this case, we can see that this is so let's say that A1, we get to trace them. A1 executes here, and then it would wait for B arrived. It would block here, okay? And B starts. B would execute B1, and after that it will do a signal. Sorry, these arrows are just got mixed up. So when it does a signal, then it would wake A1, okay? And maybe after that, it will then wait for A arrived, okay? And then this guy would wake up. It will do a signal A arrived, and then we execute A2, and then we will make a context switch. Now this wait is already signaled, and then basically we would execute B2. Now, this is a less efficient solution because in order to pass this, we need to make one extra context switch to ensure that they both pass this rendezvous portion, okay? And what about this? Now, in this case, if your statements are like both wait B arrived, if you start with wait on each side, then you will have what we call a deadlock, okay? Because A will execute A1, it will wait for B, okay? It will block in here. B would execute B1, then it will wait for A, and they will wait forever. This is what we call as a deadlock, and we will discover this later in our discussion. Okay, so you can see that even in this very simple problem, and we just have very limited number of possibilities. Ensuring that you find the most efficient solution is actually tricky, because you have to consider all the potential context switches happening in between. Now, let's make our case a little bit more difficult. It's called the barrier problem. And the rendezvous problem, it doesn't work with more than 2 threads. What if we have more than 2 threads? And that's basically called the barrier problem. And basically, in this case, every thread should run this code, rendezvous and then critical point. And then no thread should execute the critical point after all threads execute the rendezvous. Okay. And if you have n threads, where n is known, okay, then basically all of them, when the first n-1 threads arrive, they should block until the nth thread arrives, at which point they all proceed. So here is the visualization. This is imagine that you want to enter the auditorium, okay? And I want to make sure that the door will open only when all 50 of you arrives, okay? So the first one arrives, the barrier is locked, he will wait here. And as other guys come, in this case, this n is 5 here, okay? So 4 of them arrives, they will all get blocked. And when the 5th one arrives, then the barrier will unlock and all of them will proceed to the next portion, okay? Is it clear what the barrier problem is? Okay. So now let's see how we can solve this with Semaphore. Oh, okay, I still have my motivations. Okay. So here we have some hints. So first, for this, we need to know the number of threads. Okay, let's call this n. Okay, because this is we need to ensure that all of them have arrived. And count is the number of threads that are waiting. Okay, at the barrier. Then we have a mutex. This mutex would prevent protect access to count, which is a shared variable. And then we have a barrier, okay? So this is the one that will be blocked, and we will set this to 0, okay? Okay. So here's, let's see, okay. So let's look at here. So after executing our rendezvous code, we increment count by 1. This is basically when we arrived at the barrier. We increment count by 1 to indicate that, well, I have arrived here. And we do this wait and signal around it to ensure that no race condition happens in updating. Okay. And then after that, after this count, you check the count. If count is n, meaning that all of them have arrived, then we signal the barrier. Okay. If the count is not n, okay, then you wait for the barrier. Okay. So when the first thread comes, it increments it to 1. It checks it, so it through this mutex. Now the count is 1, then it will wait for the barrier. It waits. It blocks here. The second one comes, it increments it to 2, checks it, again blocks here, unless if it's like into the 5. The first 4 of them will wait at this barrier, okay? And then the 5th one comes, the last guy. He increments it. Now the count is 5. And then it will signal the barrier, meaning that, well, and then it will move on to its critical point. So it's the last guy. The last guy never waits, right? He opens the barrier and everybody should go in. Now, will this work?
No.
No? Why?
Because we wait 4 times, but signal only 1 time.
Exactly. Exactly. In this case, we signaled only once, but there were 4 threads that are waiting on it. So the remaining 3 of them will end up waiting forever. Okay, that's the problem. Now, what's the solution? Well, what about this? Is this a solution? So this, in this case, if the count is n, we signal the barrier. Else, we wait. But after wait, then we can again signal the barrier. Is this a solution?
Don't we signal one more time? I mean, an extra time.
That's good. That's good. So in this case, it works, but this is a one-time, one-use barrier, meaning that I cannot use it the next time, right? Because I will have 1 token left on the table as a result of this. So this is called a standard barrier. And actually, if you go to the little book of Semaphores, you will see that there's also the reusable barrier, which is basically which you can reuse it, in a different setting because it will clear this problem off. That's good also. And what about this? In this case, what I changed is, I have Mutex here, and I put this wait Mutex here and signal here. Okay. And what's the problem? Can you see any problem here? Well, I have already the answer in here. Sorry. So in this case, remember we had used Mutex to protect the count, right? Which was fine. Now let's say that in this case the first guy comes here, increments it to 1. Well, the count is 1, so you don't do the signal. Then you wait on the barrier. The first guy sleeps on this line. Then the second thread comes. It calls a wait Mutex, and it will wait here, right? Because the Mutex was not released. Okay, so the second guy will wait here. The third guy will wait here. So all the other threads will be waiting in the wait part, in the wait Mutex part. So again, this is not even a bad solution. This is a wrong solution. Okay. Any questions so far? No? Okay. So what I will do is I will leave it up to here. I don't want to get into the next part. Let's see if I can. Yeah, let's end it here. This is a good place to end. I know that all these things look pretty easy, but when you start working on your assignment, you will realize that this is actually really, really difficult. Okay, so I will end the lecture here. There will be no quizzes today. Okay, and for those who are still who still have their inner childs alive, I would like to congratulate, have a good 23 Nisan Çocuklar Bayramı on Friday. Okay. Any questions?
Hocam, I wanted to make a comment about the difficulty. I mean, like some of these problems are kind of solved. Like, for example, the read-write case. It's pretty simple, right? And almost every trading library will have something called a read-write lock that you can use directly instead of trying to solve the problem with semaphores. But sometimes, at least as far as I understand it, it's so difficult that people just stop trying to deal with it. Like one example, I think, was in the older days, maybe the Linux kernel just had one big lock. Because the operating system is kind of like a concurrency nightmare, right? There are all these files, inter-process communication, scheduling, etc. There's a lot of synchronization to be done. So instead of having a lock for everything, they just had one big lock. So anytime you did a system call, you lock the whole operating system. But then they had, of course, to move away from this, especially as the number of processors and systems increased.
Right.
They had to try to deal with it, right? Even though it wasn't easy. And I think this lock only disappeared from the kernel at like 2011, so it's not that old. And I have another example where this is still in use. Actually, it's a significant problem that I think many people would come across one day. Maybe, well, I did, at least back when I was a student. So for the C Python implementation of Python, they have something they call the global interpreter lock, so the GIL. So if you try to write multi-threaded Python code for number crunching or something like that, so it's probably going to be C Python. And then if you open something like HTOP, you will see that it can never use more than 100% more than one CPU, because every time one thread starts running, it locks the whole interpreter.
Oh, I see.
So you can only have you can only use multiple CPUs with multiple Python processes, like with multiple interpreters. So what I mean to say is that synchronization is difficult, right? So if you feel it's difficult, I mean, that's how it's supposed to be, I think.
No, I didn't know about those problems, but if you actually read the Green Book of Semaphores, even the names are, the problems are very interesting, like a unisex bathroom, sushi bar problem, or I don't know, like, you will see that the dining philosopher. So they all have these really funny problems, and even the the author of the book discovered that there were some problems with some of his solutions. Okay, after a couple of years, that somebody pointed them that there was something wrong with his solution. So these things are actually very tricky, especially if it's slightly more complex, and well, you will live to see that in your second assignment. So I'm very happy for you.
Yes, even debugging. I mean, usually when you have a bug with a single-threaded program, you can just reproduce it every time.
Yes,
here, you can run the program 5 times and it works. 6th time, oops, suddenly it deadlocks. Okay, well, good luck finding it and reproducing it.
Exactly.
It's not easy, yeah. But it's important, I mean. It's important, unfortunately.
So this is that's the difficult all that, as he said, each time you run, you're checking a different condition, like context switches appear in different places. And that's why, when I after this lecture, if you have time, okay, I suggest that to just pick one of the problems that I've solved here, okay? Try to solve it by yourself without looking at the answer. And you will find that it's not that easy. It looks very simple. It's deceivingly simple here, okay? But it's mind-bending. And you can only do this by solving, like understanding a solution is the first step, but it's not sufficient to pass this course. It's not sufficient to fully grasp how these things work, okay? I think that's enough for today.